Good morning, everyone. My name is Carlos Martinez, and together with Professor José-Ramón, we are pleased to present this work about CLT and concrete composite section slabs. CLT is a material increasingly in use due to a series of advantages such as its high resistance in relation to its self-weight, its low energy consumption, or the possibility of board prefabrication. However, due to the low density of wood and its low bending stiffness, it has reduced capacity to absorb airborne noise and also has low natural vibration frequencies, which can affect the comfort of users and even compromise the structure of the building due to resonant effects. The contribution of a concrete layer working alone with the CLT contributes positively to mitigate these weaknesses. Throughout the presentation, we will approach the study of the composite section according to its mechanical properties, environmental impact, and economic cost in order to apply this knowledge to three case studies that we will finally compare. For this type of section in which the materials are joined mechanically by connectors, the sliding between layers reduces the binding stiffness of the section. In the absence of a unified calculation standard, several methods for calculating the effective bending stiffness of CLT appear in the scientific literature. Thus, we proposed a method applicable to composite sections with 3 and 5 layers CLT, which we have called the successive gamma method, which consists of two phases. In the first one, as you can see in this slide, since the gamma method is not applicable to more than 3 layers according to Eurocode 5, we isolate the CLT board in which we can consider the cross layers as mechanical connectors to determine the effective inertia of the CLT according to expression 6, similar to Steiner's theorem, in which the second summand is penalized by the gamma parameter that depends in this case on the rolling shear modulus in 1890 and the H2 and H4 board dimensions. Thus, we obtain a simplified two-material section so that in a second phase we can proceed to calculate the effective stiffness of the whole section by again applying the gamma method using the expression 7, in which only the penalty due to the concrete wood connection will be taken into account. This expression depends on the sliding modulus of the connection and the spacing between connectors for the concrete layer. The next step in the study of the composite section is to determine its environmental and economic impact in order to compare it with other slab solutions. For the first aim, only the CO2 emitted during the production phase within the life cycle assessment method has been considered. If we consider a section composed of a 90 mm CLT and a 50 mm concrete topping, we obtain total emissions of 32.63 kilograms of CO2 per square meter. This is a calculation that we have evaluated for all the commercial CLT and concrete thicknesses available, obtaining the following table, where CO2 emissions per square meter of slab can be obtained by selecting the CLT thickness in the left-hand column and the concrete thickness in the top row. The same procedure has been used to evaluate the budget. This table shows the prices per square meter according to the material thickness. As can be seen, the solution is not one of the cheapest in Spain, with an average value of 225 euros per square meter. Having described the main study parameters of the section, we have analyzed these three case studies, of which we will focus on the Instituto de Ciencia y Tecnología Ambiental, ICTA, of Universidad Autónoma de Barcelona. This example consists of a regular geometry floor plan with 6.25 meters spans. For this case study, we will carry out the optimization of the composite section slab and subsequently evaluate its environmental and economic impact. In addition, we will compare the composite solution with the current solution made out of concrete, and we will do the same under the assumption of having only a CLT slab. Regarding to optimization, as you can see in the summary table in which the proposed successive gamma method has been used, the main calculation data is displayed on the left and the variable parameters are shown in orange. These are the spacing between rows of connectors and the thickness of the layers, which in this first slide are at their constructive minimum, which is to say 50 millimeters for the concrete layer and 20 millimeters for each layer of CLT board. On the right-hand side, the stress diagram and the cross-section utilization rates are shown at the top diagram. Meanwhile, the utilization rates for ultimate limit state and serviceable limit states are located at the bottom. The optimization process aims to achieve the highest and most uniform possible utilization rates of cross-section and will be carried out in two directions. For this example, we will directly check for a serviceable limit state, as it is the most restrictive hypothesis. The first option is to fix the concrete layer at a minimum of 50 millimeters and vary the CLT thickness. In this case, by opting for a 180 CLT section with external layers of 60 millimeters, we can verify that the utilization values in serviceable limit state reach practically 100%, which results in the section working below its possibilities and shown by the utilization ratio of the ultimate limit states. The other way of optimization is to set the CLT at the minimum of 20 millimeters per layer, it is to say a 100 millimeter CLT, and to increase the concrete layer, in this case, up to 170 millimeters. If we compare the results, we see that opting for the minimum concrete layer, as shown on the left, not only results in a lower section thickness, but it also provides a much more uniform distribution of stresses and makes the concrete to work exclusively on the compression stresses. We can therefore conclude that for this case study, the optimum section is composed of 180 mm CLT and a 50 mm concrete topping. Using the tables that we have just shown, we can determine that the composite section slab for this case study emits almost 62 tons of CO2, and considering a price of 208 euros per square meter, the cost per slab reaches almost 273,000 euros. Repeating the process for the different case studies, we can make a comparative study between the solutions proposed. The concrete one shown in gray, the composite solution in orange, and the CLT one in blue. Regarding to the sizing, it can be seen that for spans between 4 and 9 meters, the slenderness of the concrete slabs increases with the span due to the change from joist system with bolts for shorter spans to continuous slab solution for larger spans. On the other hand, the slenderness of the solution containing CLT remains fairly constant regardless of the span in the studied interval. Therefore, it could be concluded that for spans up to 8 meters, the solution incorporating CLT are more efficient from the slenderness perspective, but for spans of more than 8 meters, the three solutions offer similar results. So, all the criteria such as the presence of vibrations in CLT, economic or environmental impact will have to be applied in order to designate the optimum slab solution. With regard to budget and emissions, it can be seen that the concrete-based solution stands out in both diagrams as being the cheapest on the left side and one of the most polluting on the right side graph. On the other hand, the composite section slab and the only CLT one present very similar results, with the composite solution being around 50% more expensive. This difference is practically constant for all the study cases, which means that the budget grows linearly, what doesn't occur with the emissions, given that as the span increases, the emissions between CLT and the composite section tend to converge. With this data, we can draw a series of conclusions about the CLT concrete composite section slabs, in addition to those we have already discussed in the optimization section. Regarding to the CLT concrete solution, from the point of view of dimensioning, it offers greater slenderness than concrete slab for spans of less than 8 meters. In addition, the CLT edge in the composite solution offers slightly lower thicknesses that only use CLT, without going into vibration and noise absorption, which is beyond the aim of this work. In terms of budget, it is clear that reinforced concrete Slabs are currently the leading solution in Spain, given that building with a composite section increases the budget by up to 140%. At the same time, the mixed solution is only 10% more expensive than a CLT slab. Lastly, in terms of pollution, the composite solution offers significant reductions in emission compared to concrete, and it is not much more polluting than CLT. In short, we could say that the combination of concrete and CLT in slabs for residential and administrative use offers several advantages, and although it is far from being a conventional solution in Spain, mainly due to the cost, it could be a way to combine the benefits that both materials offer in favor of a more efficient architecture. That is all, so I hope that you have found it of interest, and thank you for your attention.